Hey, what's up, guys? So today I want to talk about Stirling formula, and this is very old topic, but seldom people, unless you're a mathematician or otherwise, seldom people have done the actual derivation. Okay, so I will highlight different kind of from step by step, and finally we will arrive the standard Stirling formula. Okay, so the use of Stirling formula is a very has very various process. For example, you can use Stirling formula to apply to the application on binomial coefficient. Okay, well, and also applying the random walk. Okay, so let's do the approximation. Okay, so the idea is that how to approximate n factorial. Okay, so let's do it simplest way. Okay, so simplest way is very simple. So simple that you know that if you do a Taylor expansion, right, then you know this. Right, so obviously that when x greater or equal to 0, your xn divided by n factorial or less than equal to exponential x. So you get exponential n factorial greater than exponential n, right? If you put, what I was writing. So if you put x equal to n, you get n to n factorial less or equal to exponential n. So n factorial will greater or equal to n to n divided by exponential n. Okay. So this is the first one. And also trivially, you know that n factorial is 1 times 2 times n up to n. So n factorial less or equal to n to n. Okay, so this is the trivial upper bound and lower bound that one can easily get just using the standard calculus. Ooh, okay. And but this is not so good, right? So let's redo. Okay, so that's the second kind of approximation. Okay, so second kind of approximation that you can start from a simple log n factorial will be, right? Just take log summation n from 1 to n log n. Okay. So idea is that we can use the integral test. Okay. So if you use the integral test, you get 1 to n log x dx, right? Use your integral test less or equal to log m, and from 1 to n. You can draw this as a picture, and this guy is less or equal to log n plus n1 log x dx. Okay, so this is the integral test that you can easily do. And the log x dx will be x log x minus x. Okay, so using your simple calculus, you get your, this is log n greater or equal to this. And log n plus 1. Okay, so combine everything, you can get, if you take exponential, you get n factorial less or equal to exponential n times n to n times exponential negative n. And for this one, you get n to n, right? So n to n, and then take e exponential negative n. Okay, so this is one of these, right? Let's see. Yeah, you take exponential n. Yeah, so you take exponential n. Yeah, okay. Let's see, right? So you can take exponential. Let's say this is. Oh, sorry, I'm stupid. Right, so you need to do the minus n, right? Minus n, right? Because this is n log n minus n. So I just forget about this n. Okay, so then you take exponential that you will arrive this, right? Because this term will give you this, and this term will give you maybe this. Oh, there's a minus 1 here, right? So you should add 1. Okay, so let me just write clearly again. So you get this plus 1, that's equal to n factorial. Summation n from 1 to log m, and also n plus 1 log n minus n plus 1. You take exponential, so you get this is n log n, sorry, n to n exponential negative n minus 1, and this is n factorial. This is okay, so this is right. You do the same thing, and for this one, you get the same thing. and you get en has n to n. Okay, because it comes from this. Okay, so this is the second derivation of the second kind of bounds that you can get from the simple formula. Whew. Okay, so the third one, basically you can use trapodized rule. Okay. Okay, so the trapodized rule, you can take, let's say, if you take interval from m to n plus 1, and you x n plus 1 log x. So you can take a f of x dx a b, right? Approximate as a b minus a, and the f of a plus f of b divided by 2, right? This is the approximation. You can see a picture like this, right? So basically it's a and b. This area can be approximated by b minus a times the average value. B minus a and maybe this, right? And you take something like this. Okay, so you can approximate this as a half log m plus a half log m plus 1 plus some let's say epsilon m. Okay, and the epsilon m is the secondary differentiation, right? So basically it's the order of 1 over m squared if you take the differentiation. Okay. Now you just take n from 1 to n and get your summation. You get 1 to n log x dx is that great. It's just n from 1 to n minus 1, and you combine these two terms, you get log m plus a half log n plus c plus o 1 over n, right? Because summation of 1 over m squared is converged. Okay, so this is all you get, all you can get. Okay, so now you do the same thing, right? This is n log n, so this is n log n and minus n, and you take the exponential. Okay, so take the exponential. Okay, so you get n factorial is basically 1 plus o 1 over n. This is big O, e 1 minus c square root of n exponential negative n. Right, so this is already very famous, or very close to the standard form, right? This is the standard form, right? So see, you can see a square root of n, and then these turn out the same, and also this minus but this is constant term, right? Okay, so these are very close to the usual formula. Okay, so the most famous formula is this one, right? This is you need to solve, you need to prove this by using the gamma function. Okay. Okay, so the final one, okay, is that you can take n factorial into 0, infinity, negative t to n dt. So this is a famous gamma function. This is gamma n plus 1. Okay. Okay, we need to do the calculus, right, on this term, right? So if you do a differentiation, then you know that when t equals to n, then this guy should leave the maximum, should become the maximum. So we need to do an approximation close to these points. Okay, so the standard trick is that you just let t equals to n plus s and then put in. Okay, so we get n to n, let's say n to n exponential minus n exponential negative n, and then you do a trick, right? So it becomes just 1 plus s divided by n. Okay, so this is just the change of variable, right? So just do this when t equals 0, that s equals to negative n infinity, and t to the n is just n plus s I divided n to n because okay. Okay, so all what we can do is what we just try to put everything on the exponential. Okay, so this is a trick. Okay, so we can just do the n log. The trick is that let's do this, right? One can just write this in terms of combine this, right? So this is exponential, and 1 plus s divided by n. Sorry. Right, so it's log 1 plus s divided by n and minus s. Okay, so ds. And then we need to do a Taylor expansion on around s equals 0, right? So let's do this. So this is just s minus s squared divided by 2n. Okay, so heuristically, you can easily write this guy as a in infinity, negative n, and exponential. Right, you just do this, right? It'll become this. Okay, if you take the n to be infinity, then this guy is a famous result. You become this. Right, it becomes something like this, right? So when n is very large, then it becomes square root of 2 pi n. Okay, so hopefully, let me check. So remember, it's this square root pi, and then you put a here, it becomes divided by a, right? So it should be square root pi divided by square root of 2 pi n. You put in, you get the standard results. Okay, so this is heuristic proof, and now we need to, but this is heuristic, right? So hopefully we can get some rigorous proof. Okay, so rigorous. So at least I should say, more rigorous. Okay. Okay, so remember that's we just guide, right? So we very, very close to this one. But let's go back to here. Okay. So let's make s equals square root of nx, and one can show this. Okay, so one can show this. Just make a change of variable. Okay, it becomes square root of n. Okay. Okay, so now one can use the Taylor expansion. Okay, so the trick is that so you can just do a trick on this, right? But actually you can use a theorem of fundamental calculus to show this. You just do the differentiation on x, and you get this. Oh, this is so amazing that using this you can always change the minus in terms of differential into the integral, right? So now you can try to bound these terms. Okay, so obviously that whatever y, right? This guy, if you take I take absolute value, so this guy will less than some cx squared, right? Because if I make y to be just do the neglect these terms and do the integration, then I get something x squared. And there's should be negative sign, right? Negative sign here. So this term is definitely converge. Okay. Okay, so now I can take the big dominate convergence. Okay, so the rigorous proof comes here. Use the back dominate convergence. Dominates convergence theory. This is the LDCT. Right, so this is a famous theorem that in the real analysis, if you haven't seen the proof, then I will post my real analysis video list below so you can check the proof. Okay, so this guy is bounded. So if I take n to be infinity, then this guy can converge to what you want. Okay, so basically it's this. So this is the actual rigorous proof, which comes from here. Right, if you take n to be infinity, so since this guy is bounded by some, is bounded by this, right? So I can use the LDCT and directly exchange the limit and the integral. So LDCT tell me that I can exchange limit integral. Okay, so n goes to infinity and everyone is happy, right? So this guy becomes this. Okay, so this is a standard trick, right? So square root of 2 pi. Okay, so if you put square root of 2 pi and it goes square root of 2 pi and goes to infinity, then you get a standard bound. Okay, so finally, we arrive our results. We arrived the 100% rigorous proof of this. There is a small one. This is a trick that you need to do some more work to prove this is true. But more generally, you can just do a very simple analysis on this kind of terms and take n to be infinity, right? And the LDCT give you a square root, but you can estimate this bound by via the square root of n. And there is some detail, but basically this is the proof of the Stirling formula. Okay, so see you guys next videos. Hope you guys subscribe to my channel.